Hello, I'm Sean McGee, and I'm an astronomer and a faculty member at the University of Birmingham. I research how galaxies form and evolve through cosmic time, from the Big Bang at the beginning of the universe all the way until today. In this talk, I'll tell you about a new type of galaxy that astronomers have found, and which are called ultra-diffuse galaxies. I'll then discuss these galaxies and whether they're a challenge for what we know about the universe and how galaxies form. A slight spoiler alert is that we don't have the answer, because this is still an active area of research. So if we go in to see what a normal spiral galaxy looks like, it has a distinctive arm pattern like this one and like the one behind me, with sort of bright patches where current star formation is happening. These galaxies tend to be much brighter near the center than in the edges. In a sense, they're more concentrated towards the center. They have this concentration. But they're also fairly bright all throughout the entire galaxy. You can easily pick them out against the background, and they make the nice images that people see. So in the last 5 years or so, astronomers have sort of characterized another kind of galaxy. It's been known a little bit before that, but it's only recently that we've really got these in large numbers. And this is shown in this picture in the middle. You may notice a sort of faint, fuzzy kind of galaxy in the middle. It clearly looks sort of different than that first galaxy. These two galaxies have about the same physical size. The images are sort of scaled similarly. But a normal galaxy is much denser and brighter than this ultra-diffuse galaxy. And it's this feature that makes this galaxy called ultra-diffuse. It seems much more spread out than normal. And as I said, I'll talk about whether or not this is a challenge to galaxy formation. But before I can discuss why this kind of galaxy is unusual, I'll describe first about how normal galaxy formation happens. And there's really two elements to galaxy formation. The cosmology part of it, or what our universe is sort of made of. And then what is also sometimes called gastrophysics. And that's really sort of the astrophysics of normal matter, like gas. It involves a lot of different, very complicated physics, if we're honest. Kind of like the formation of stars, the radiation that such stars give off to their environment, and the energy that these exploding stars give to their surrounding gas, and even things like the exotic effect of, say, matter falling into a black hole, getting heated up and just sort of spewing back out. So we'll look at each of these in turn, ultimately understanding how normal galaxies form. So the first tenet of this is cosmology. You may have heard that our universe has only about 5% of its total energy densities in normal matter. And that includes things like, the sun, the moon, trees, and chairs. These clearly have a big impact on our lives and also about how galaxies form. But for the most part, a large part of galaxy formation is caused by gravity. And that gravity is really dominated by dark matter, the stuff we don't see. And where the stuff we see, the ordinary matter, is really like a frosting on top of that. So we'll first talk for a minute about dark matter. Since it's sort of the dominant cosmological force on galaxy formation. So this is an image taken from a numerical simulation, which can follow the growth of a substance like what we think dark matter is. When these simulations are done, it turns out that dark matter, if you just let it be and form through gravity, clumps together in a very particular form called a halo. Notice each of these sort of spots in the image, or these clumps. These are each collapsed halos that have formed out of initial very smooth matter density distribution in the very early universe. Those very small ripples that happened in the early universe, these initial seeds that eventually formed these halos, is really thought to be caused by tiny, tiny quantum mechanical effects, which were essentially blown up into a massive size through the process called inflation, which I won't talk about. And those really form the basis of the galaxies we know today and the collapsed structures. And we believe basically that every galaxy forms at the center of a dark matter halo. And this is one of the central tenets of galaxy formation, and something that may be, challenged by ultra-diffuse galaxies. But it's first useful to sort of understand what the evidence for dark matter is. I mean, astronomers say it exists, but you shouldn't trust anyone based on just their opinion or what they state. You need to see the evidence behind it to see if you follow their reasoning. And the evidence for dark matter really started to convince at least the bulk of astronomers that dark matter was real, and it came from the work on rotation curves by astronomers such as Vera Rubin, who's shown here in this picture. In the 1970s, these astronomers made really careful and crucial measurements of how fast stars moved around the center of a spiral galaxy. And the speed of those stars moving in the galaxy tells you exactly how much sort of gravitational force they're experiencing from the matter closer to the galaxy's center. If a star moves faster in a galaxy than the gravity can maintain, it will just fly out of the galaxy. And you can kind of think of this like a person being spun around on a carousel. If you spin them too fast for their grip to hold on, they'll just fly off the carousel, which is not something I'd recommend, but And so by necessity, if you see stars spinning around, they can spin no faster than the gravity can hold them, else like the person in the carousel would have flown off. So in this plot on this slide, you can see the circular velocity, that is how fast stars are spinning, versus the distance to the center. The data points are the black points that you can see. And it turns out that you can't explain those black points, that is the rotation speed of stars around a galaxy, if the only material in the galaxy is the stars. If that was true, you'd predict a rotation speed that would fall off pretty dramatically with radius, get slower and slower, as the sort of disk line in this plot shows. The data seem to require an additional mass component, and here that's labeled as halo to explain the data. This halo, you can't see it through a telescope other than this kind of indirect effect. And this is really the beginning and the basis for dark matter and what we call dark matter. Although it's popular to talk about galaxy rotation curves as the reason for believing there's dark matter, I should note that there's also dark matter has sort of beyond those the evidence for those has really become sort of overwhelming from different observations. And more generally, all different aspects of our current cosmological model are really well understood. So today we know about things like dark energy from the brightness of supernova explosions and their brightness as a function of the distance to them. We have good evidence that the dominant gravitational force of cold dark matter really dominates the large scale structure. And we can see that both in simulations and observations and comparing the two. Similarly, the cosmic microwave background gives us a picture of the universe soon after the Big Bang and sort of before any of these large scale structures have collapsed. Our cosmological model really seems to all fit together, and together with the abundance of elements that are predicted by Big Bang nucleosynthesis, that is the production of elements soon after the Big Bang, when the universe was very hot and dense, they all really fit together well. And the interesting thing is that they all probe quite different circumstances in the universe. If you think of the Big Bang nucleosynthesis, it's right after the Big Bang where the universe is very hot. The CMB, or the cosmic microwave background, is sometime later, but in the very flat stages of the universe. The large-scale structure is essentially today, and the supernova you can see throughout time. All of those things sort of come together to make the cosmological model we know. And so it's important to realize that disproving sort of one part of that thing will still leave the whole sort of relatively cohesive. And so that's what why we call our cosmological model the concordance cosmological model, because everything sort of seems to fit together pretty well. So now I'll talk briefly about the other side of galaxy formation, and namely the gastrophysics part. This is an image of a region of forming stars, and you can immediately see how it's very complicated. There's swirling dust clouds and strong clusters of emission, which is the basis of star formation. And so overall, the cosmology sort of describes how dark matters grow and in what abundance. But what happens after that in the galaxies is really the realm of this thing called gastrophysics. So mixed almost uniformly through the dark matter halo at early times is this gas, which makes up the normal baryons and the normal stuff. The interesting thing about that normal material, unlike, say, dark matter, is that it can interact with itself and also give off photons. This means that the gas and the normal material can ultimately cool. And when a gas cools, the individual particles stop moving as quickly. And as they do, they no longer orbit as quickly through the dark matter halo and tend to sink to the bottom and sort of clump together. This means that, with time, as gas cools, it will clump towards the center of the halo. And if it cools enough and clumps enough, it'll eventually be dense enough to form individual stars. These stars then ignite nuclear fusion in their center. And with the accumulation of those enough gas and future star formation, the halo essentially hosts a galaxy at its center. That's the accumulation of those stars is a galaxy. And with time, the more gas cools through these processes and the galaxy grows bigger and bigger. And at some point there, the galaxy naturally begins to look a bit like a spiral galaxy with a bright center where all the stuff is sunk towards and arms of star formation swirling around it. There's a whole wide range of other aspects of galaxy formation that come into play here to determine exactly what these look like. Galaxy formation is not a solved problem or a solved field, and there's lots of things that happen. But some of those are explosive things like we talked about earlier. For instance, this image of this particular galaxy looks mostly like a normal spiral, except that you can see these great hot plumes of red gas coming out perpendicular to it. This gas is expelled from the galaxy and outflows. These outflows are thought to be from things like internal feedback mechanisms, sort of like supernova explosions or this black hole emission that I talked about before. Ultimately, in a detailed process that we don't fully understand, galaxies tend to form a very regular structure that falls on sort of consistent scaling relations like the one shown here. This plot shows the size of a galaxy on the y-axis versus the total luminosity of the galaxy on the x-axis. The two types of galaxies, early, meaning sort of round and elliptical galaxies, and late, which sort of mean like a spiral galaxy. They both have well-measured relations, which are pretty similar to each other. And you can see that a brighter galaxy, so you go to this side of the plot, tends to be bigger and is consistent through a wide range of luminosities. So the same relation seems to hold throughout the whole range of luminosities. So somehow these aspects, the gastrophysics, the detailed structure, and cosmology work together to produce these galaxies. And we think we have a reasonable understanding of why that is. But these are very fundamental parts of astrophysics, right? Gas physics and cosmology. So when something sort of weird shows up, it's very exciting. And now I can talk about ultra-diffuse galaxies and what they are and how they were found. This plot is similar to the one I just showed. It plots the size of a galaxy versus the total luminosity or the brightness of the galaxy. These gray points are sort of normal galaxies and the kind I showed on the previous plot. The surprising thing is these red points. They're what's called ultra-diffuse galaxies, and you can see they have a larger size than you'd be expected from their brightness. Right? See, they're up in this region. And although galaxies of this type have been known for a little while, a new kind of telescope called the Dragonfly telescope started to find and measure these galaxies in really large numbers. And so now these galaxies are actually routinely found all over the sky thanks to improvements in sort of data reduction techniques and as well as sort of a concerted effort to figure out what they are. And if you remember a couple of slides ago, I said one of the characteristics of normal matter in a dark matter halo is that it sinks to the bottom and forms a concentrated object. These very broad, diffuse nature of these particular galaxies then maybe points to them as strange objects. Why aren't they more concentrated? There's lots of interesting aspects to these galaxies, but one of maybe the most exciting is that people have suggested they don't form inside of substantial dark matter halos like most galaxies. If we remember back earlier, the initial evidence for dark matter from Vera Rubin came from measuring the speed of stars around the galaxies. In this case, our current telescopes can't actually measure the individual stars. They're too faint. But luckily, we have objects called globular clusters, and these are very, very packed, dense regions of stars. And in this case, they sort of clump around and through ultra-diffuse galaxies. With today's telescopes, we can measure the velocity of each of these clumps and try to tell how much matter must be holding it together within the galaxy. These globular clusters are shown in the image, and they're noted sort of by these individual numbers. You can probably just make them out as like bright points on the plot or the image. And so if you go and measure the velocity of each of these globular clusters, you can get a dispersion of velocities around the galaxy. That is, some are a little bit in front and moving towards, and some are a little bit away and moving back. And that dispersion tells you the total mass in the same way that the velocity around the galaxy does. And so here's a histogram of the velocity of each of these clumps, that is those globular clusters. And the red line is a fit to the data. And it suggests that they're only moving around the galaxy at about 8.5 kilometers a second. Although, 8.5 kilometers a second sounds very high. In the context of galaxies, it's actually really pretty slow and suggests that there isn't much mass within this galaxy. A way of seeing that is in this plot, which shows the velocity dispersion versus the mass of the stars in the galaxy. This is shown for a wide range of systems, but the particular galaxy that we're talking about is shown here around the 8.3 stellar mass mark. Notice this dotted white line. This is the velocity dispersion that'd be expected if the velocity was only due to the mass of the stars that we know about, the ones that we can see. In other words, that there's no dark matter in this galaxy. That would be the implication. And that's sort of the implication that we have at the moment. Another way of seeing that is in this plot, which shows the velocity dispersion together with these sort of shaded regions, which is where you'd expect the galaxies to be if they contained only stars on this side, or if it had a normal dark matter halo and looked more like a normal galaxy. It should have a higher velocity dispersion up at this area. And so this is a very active field, active area of study, because it's potentially so exciting. And so you can see there's also been 2 further studies of this galaxy, these 2 other data points with different techniques, but which verify the velocity dispersion measured. So it's clear that it wasn't just a fluke of that one particular measurement. We think this is really that velocity dispersion. And this really suggests that, dark matter doesn't exist as much in this galaxy as we'd expect, which is really exciting. But perhaps even more exciting, because there's you can always explain one object maybe. More exciting is that there's a second ultra-diffuse galaxy which has been found, which also seems to have a lower than expected velocity dispersion and may point to dark matter not existing in that galaxy. The lines in this plot show the expected velocity dispersion, which comes from analyzing this new data. And the red line is what is expected if only the stars exist in the galaxy. Again, this seems to be another galaxy which just lacks a dominant component of dark matter, which really suggests maybe in general, these ultra-diffuse galaxies don't host dark matter, which would be very exciting. And so these findings are very exciting, but it's still an open area. This is relatively early days on this study, and we don't know yet exactly what's driving this formation of these galaxies. Although there's many possible explanations. For instance, you could imagine that the galaxies are simply failed Milky Ways, that for some reason they haven't formed as many stars as you'd normally expect for their size. Although this might explain them sort of generally, their processes, it wouldn't explain why they seemed to have no dark matter. If it was just a failed Milky Way, you'd expect the dark matter halo to still be there, but just the number of stars to be fewer. And doesn't seem to be the case. Another explanation for this could be that they were disrupted by other galaxies, which essentially puff them up by interacting gravitationally with them. That's possible. Another explanation is that some kind of internal processes, maybe like this black hole feedback, has caused the galaxies to form very differently. For some reason, these particular galaxies maybe have formed differently. Fortunately, neither of those two explanations would explain why there's a lack of dark matter. If there was some internal process that stopped it, the dark matter should still be there, and if it puffed up by interacting gravitationally, it probably also should have a dark matter halo. And so none of those explanations are really terribly satisfying. And so it maybe leaves the question that there's something completely different that needs to happen to explain these galaxies, and maybe a complete revision of our picture of galaxy formation. Luckily, we won't have to wait too long to make a lot of progress. In the future, I expect with new telescopes and new observational techniques becoming available, that we'll find a lot more of these galaxies and really start to understand what's happening. One of the telescopes I'm personally most looking forward to is the Rubin Observatory, which is currently being built in Chile and should be available in the next couple of years. One of the first surveys this telescope will do is called the LSST, and that should be a really interesting survey for this. The telescope has a very big mirror, but can also take images of very large regions of the sky all at once, which means we should be able to detect these ultra-diffuse galaxies with, extraordinary speed and number in the near future. One of the things I like the most is that the telescope is named after Vera Rubin, who I mentioned earlier really pioneered the study of dark matter in galaxies. And so at least to me, it seems fitting that the telescope that bears her name will take these studies much further into the future. So that's ultra-diffuse galaxies. And as I said, we don't really know what happened or why they are like that, but it's a very exciting time to look into them.
Right. Hello and welcome back, everybody. Really glad to see you all joining us again, and hope you enjoyed the talk from Sean. It was absolutely fascinating as usual. We're trying something a little bit different this week. So instead of you joining the Zoom call, as explained in the email, we're going to take the questions via the chat, the YouTube chat. Anything that pops up there, one of the committee, either myself, Amwesha, or Eleonora, will then ask those questions to Sean, and we'll see what he can answer for us. So at the moment, there doesn't appear to be any questions, so I'm going to open it up to the committee. But please, if you have any ideas, anything you want to ask, that would be absolutely great, and we look forward to kind of engaging with you. Here we go.
I guess I have a couple of questions to kickstart the discussion while we wait for some more questions from the viewers. The talk was extremely engaging, and I found it really exciting to learn more about ultra-diffuse galaxies. It's definitely something that it's quite new to me. And I was just wondering, since we discussed a bit about dark matter in the talk, how is dark matter detected in modern astrophysics?
Yes, so in a bunch of different ways. You can hear me okay? Yeah, in a bunch of different ways. So one way, I guess, is through its presence it always has to do with the presence of gravity on things that you can't see. So because basically, as we know it now, it doesn't have any other properties other than its gravitational force. So you can see things that have gravity in terms of like large galaxy clusters. They have it implies they have a lot more mass than we can see, mainly like through the X-rays and things they give off. They're at a much higher temperature than they would be if there was no dark matter. And you can see it through, I gave a bit of a talk about that in the about spiral galaxies and the rotation curves, and how in the rotation curves, really they don't drop off with distance from the center like they would if you expected that to be just the luminous matter and not dark matter. And then they can also detect it basically from things like in the early universe, we know how many. We can basically look at the CMB, and the size of the fluctuations in the CMB give you some indication of how many regular baryons there are. But you can also constrain how much total mass there is, and the difference between those two really implies there has to be some kind of dark matter.
You mentioned obviously you mentioned different types of galaxies, so spirals, and some of us may know there are also elliptical type galaxies as well. Do these ultra diffuse galaxies have any sort of structure that we can see? Do they fall into one category more than another? And could that be a reason for them possibly containing no dark matter, or certainly very little dark matter?
Yeah, so it's not clear. The problem with them is that partly because of like their name, they're so diffuse that it's very difficult to get any other parameters about them. It does seem like they, you can sort of look at the light profile. And so we think of spirals and ellipticals as being different because one has the spiral galaxies and one sort of looks like a blob. But if you just looked at the light profile, so how much light from the center to the outskirts, the ellipticals drop off a lot quicker. Like they decline much faster with radius than the spirals. And the ultra diffuse galaxies seem to be pretty close to the spirals in terms of their light profile, how it drops off. And so that seems to suggest that they're more like disk galaxies than ellipticals. It's still a bit of an uncertain issue, but that certainly seems to be part of it. And then that makes it a little bit actually more difficult, because you could maybe see that if things were forming through mergers, they may have disrupted the dark matter around it or something. But if they're forming like regular spirals where you just have the gas come in and form stars and form this diffuse material, then it's more difficult to see how that happens in the absence of dark matter. Yeah, so it is a bit of a problem.
Can ultra-diffuse galaxies then, can they be part of regular galaxy clusters, or do they have their own types of galaxy clusters? Like, do they form clusters in general, I guess?
Yeah, that's interesting. So they're in normal galaxy clusters. That they were first found basically in galaxy clusters, but the reason is just that it's easier to see them there because there's more galaxies, and you could just point a telescope there and there's going to be something there, where in another part of the universe there's less of that true. And that's why actually galaxy clusters have been really good for galaxy evolution studies in general, is because basically you can point your telescope there and you always get a bunch of galaxies. And we actually wrote a paper about how these ultra-diffuse galaxies are in different types of halos, like clusters. And we showed that they're less likely to be there in low mass halos. The problem is, as you said, if they form their own clusters, we basically wouldn't easily be able to see them, because you wouldn't sort of know they're there, because they're so faint that you have to look for a while and then do some processing to see them. It may be difficult to see them if they're on their own and know that they had been there. But it's an interesting question that I think it's something I'm actually interested in doing and seeing whether it's true.
So it looks like we have a question from one of our viewers. So they have asked, in ultra-diffuse galaxies, is there enough evidence to suggest an abundance of dark matter? No, sorry, an absence of dark matter. Or is it more likely that it is merely a reduced ratio of dark matter to regular matter?
Yeah, I mean, I think that's probably true. So there's this, this famous saying that the absence of evidence isn't evidence of absence, right? And it's the same kind of thing here, really. You can look at the ultra-diffuse galaxies and they have low velocity dispersions, which suggests they don't have much dark matter. But that doesn't really say there's none, right? And it also doesn't really say there's really much less, how much less there is than normal. In particular, you could imagine that if they're distributed differently, so that the dark matter sort of isn't as condensed as the ultra-diffuse galaxy, maybe that ratio is changed. And so you could probably mimic some of this with a reduced ratio rather than an absence completely. And I think that's an important thing to remember, yeah.
So we heard last week from Dr. Matteo Bianconi about quenching of galaxies in galaxy clusters. Is there any possibility that actually what we're seeing is a stripping of a lot of the gas and perhaps even stellar material, even stars, where actually the dark matter continues to fall into the gravitational well of the cluster, and what we actually see is the remnant of this? Obviously, I'm presuming that would only work within clusters. So if we saw ultra-diffuse galaxies outside of clusters, that may be an issue. Is that something we see?
Yeah, exactly. That's definitely true. So one of the earliest ideas for what they are is that they basically are things that fell into clusters and then either got heated from like interacting with the other galaxies, or this tidal stripping and the loss of gas. And that was pretty popular at the time, especially because a lot of the galaxies in clusters happen to be or are caused to be quenched, right? So basically everything in the cluster is quenched. And so when you were originally finding these ultra-diffuse galaxies, they were also all quenched for the most part. And so it could easily have been the case that these quenched galaxies, that was the result, but it's almost very hard to disentangle which of those is true. And it turns out that exactly what you said, that if you find them in the field or not in clusters, that's a reason to suggest they aren't caused by that. And we basically have detected them in the field. It's very difficult now to figure out exactly, because there's a couple different ways of looking at galaxies, right? One is through images and the other is spectroscopy and getting the redshift. And it's really difficult to get the redshift for most of the galaxies because they're so diffuse. And so we can see there's things that don't seem to be in clusters, and you can make arguments that they're in the field, but it's, for the most part, it's difficult to tell that they actually are in the field rather than in some other line of sight or something. But yes, basically, I think it was an excellent explanation for it, except that we see them in the field, and so that's probably not the case.
I was just wondering, is there the possibility of there being ultra-diffuse galaxies that are not in the visible spectrum? So for instance, any like possible stars or, like gas bodies which do not emit in the visible spectrum, and how would we go about detecting these?
Yeah, that's right. So there are things, so one of the best ways to detect these kinds of things that aren't optical is through their neutral hydrogen gas, so H1. That neutral hydrogen is like, because it's essentially, hydrogen is the most abundant element in the universe. The neutral hydrogen is therefore the most abundant thing. And you can have this neutral hydrogen measurements through radio telescopes. And so people have done radio observations of the local universe, and you can find galaxies that clearly have lots of H1 gas, but don't seem to have optical. And the problem is it's difficult to know whether they're diffuse as well. You just know that they exist and they don't have much optical counterpart, but not necessarily that they don't have, that they're diffuse. But they're interesting objects, and maybe they're sort of related in that same way to ultra-diffuse galaxies.
We, later on in the talk series, I believe we're going to hear potentially about gravitational waves. Now, for those of our viewers who don't know, gravitational waves are strongly linked to things like black holes, although they can be from other things. And those of you who may know that most galaxies, and certainly our galaxy, has a black hole in its center. These black holes have possibly been linked to dark matter in a variety of different forms. So do we know if these ultra-diffuse galaxies contain black holes either within them or situated at their center?
Yeah, we basically don't know. And the reason is they're just difficult to detect. So the main way we know the black holes exist in galaxies that you can't see directly are through things like X-rays. They're X-ray emitted. And if you take the size of these galaxies and the size of the black holes they'd have, you mostly couldn't detect those things. And so we don't know, but that doesn't mean they don't exist in the same kind of way, which would be really interesting because it may tell us a lot about how they form.
On a cosmological timescale, would normal galaxies or would ultra-diffuse galaxies be the more recent ones, or do they generally form around the same times and there's no specific bias towards which time they would form in?
Yeah, so they probably form around the same time. The problem is it sort of depends on the definition of what forming means, because one common definition of forming just means the time at which it formed half of its mass or something. Because these things are almost no galaxies, maybe some very massive ones in the very early universe form really quickly, but most of the time they have extended lifespans over most of cosmic time. And so then the question of exactly their formation time isn't very well defined. It may mean that you can make, then you can look at like if their track is typical to other galaxies. And it seems like spiral galaxies or lower mass galaxies tend to form a little bit more recently in that sense than older elliptical galaxies. And so if these ultra-diffuse galaxies are like that, they're probably also formed more recent than the early elliptical galaxies.
In that case, is it possible for there to be galaxy mergers between, let's say, different ultra-diffuse galaxies, or an ultra-diffuse galaxy and a regular galaxy?
Yeah, they certainly could. I think actually one of the other scenarios for how these things formed is what's called tidal debris galaxies. So if you have two normal galaxies and they merge together, you could actually send off a smaller part of a galaxy that then stays itself as a galaxy. And so that could be an ultra-diffuse galaxy eventually. It's one of the formation mechanisms. But then if that was true, that galaxy could easily then come back later and merge again, or merge with something else. So they should have the same sort of merger rates and things as most normal galaxies. Certainly what that would look like for two ultra-diffuse galaxies merging, and whether you'd actually see it or not is not clear to me, but
it looks like we're coming up to nearly the end of the allotted time that we've got. So I guess we'll look at taking one more question if anybody has one.
I guess I just have a rather vague question relating to the research that goes on in our university. So in terms of the research at the University of Birmingham, do we have any specific projects that students could potentially engage in for dark matter or ultra-diffuse galaxies?
Yeah, I mean, there's lots. So one of the as I mentioned there at the end, one of the big things for this area is going to be the Rubin telescope, or the LSST, which the University of Birmingham and other places in the UK are also involved in, and that should become available in the next couple of years, a year and a half or something. And those are really going to be great places for students to get involved. But there's a lot of preparatory work and things before then that they could easily help with in terms of using other data to simulate it, or numerical simulations, that kind of stuff. Yeah, there's always more work than people usually.
Brilliant. Thank you very much. I think that is going to be everything by the looks of things. So we'll look at closing the session out now. Thank you to all our viewers who have joined us this week. We hope you've enjoyed the talk and found the answers that Sean has been able to give us really enlightening. And hopefully you'll join us again for our talk next week. Thank you very much.
Thank you.
Thank you.
Right. Thanks.
Thank you.